In this video, we're going to talk about something called zero shift. This is an option in a laboratory. It's an option on the computer software. And a lot of people think that because it shows up in the computer software systems that operate the equipment, that we can do it and get by with it and do what we need to do. The problem, though, is that this could actually deviate your answers from the calibration curve. So I want to talk about what zero shift basically means and why you should not be using zero shift most of the time in a laboratory. So let's say that we generate a calibration curve, and this calibration curve has a set of standards. Now, normally this would go through the point 0, right? So I would make a set of standards, and hopefully I would get something that looks like this, and I would get a straight line that goes through the point 0, or at least close to it. So zero shift is basically this concept of the linear regression line going through the point 0. If it goes through the point 0 or something close to it, then this is a prim and proper calibration curve, right? So we said that this is the purpose of the blank, and the blank is typically the solvent. And sometimes they call this word the matrix, all right? So it's typically the solvent, whatever your sample is being dissolved up into, or whatever you're using to dilute your samples with or your standards with, that is the solvent. That's what's being used as the blank. There's nothing else that should be present. And sometimes we said that we get a very small signal from that blank. Well, that's okay, right? We know it's not going to be zero perfect, but it could be really low. And if it's really low and close to zero, then that's fine. We might be a little bit above or a little bit below the zero mark. That's okay, because we can get a positive signal and we can get a negative signal, especially something that low. We basically have nothing present. If the instrument is not tuned perfectly, then we could go on the negative side of the zero instead of the positive side. So no big deal if it happens, right? We run the blanks, we process it just like a standard, we make a calibration curve with it. The problem, though, is that sometimes the solvents, they can contribute quite a bit to the signal of the instrument. And most of the time, we're talking about absorbance or we're talking about areas. I keep writing this over and over, and you're going to discover that in the instrumentation courses, what I mean by that. But the absorbances and the areas could be much greater than zero, right? So these could be like 0.1s and 0.2s. And the question is, how do we handle them? Because if that solvent is contributing that much signal, then it's contributing that much signal to every single standard as well. So here we have basically an issue. And the issue is if we run those blanks, that blank might start up here instead of down here close to 0. And then all of my other standards that I have made will also run higher. Okay, so that means it runs higher here, and it runs higher there, it runs higher here, it runs higher there. And we still maybe could end up with a straight line, but it's not going to go through the point 0. So some people in the past have looked at this type of calibration curve and said, you know, that's proper, we can do that. That's not an issue, right? Because everything is proportionate, which means that if I use this solvent in every single thing that I do, it's going to basically wash out in the end. Sure, we're getting a signal in the very beginning that's a little bit higher than expected, but that solvent is also used in every single volumetric standard that I'm making. So I get this regression line. It just doesn't go through the point 0. I can still get a y equals mx plus b for that new line, and we can still use that equation to solve for our samples as long as the samples have been processed with the same type of solvent. Well, here's the problem with this. Back in the day, they used to call this zero shift, which basically meant that we could take the concept of this solvent running a little bit higher, and we could move this line downward. And when we do that, we could force that calibration curve to go through the point 0 because of that. That's why we call it zero shift. We're shifting the calibration curve down to make it go through the point 0, 0. This works okay when the signal is very, very small with our solvent. So if we're working on the 0.02s and the 0.01s and we're really close to 0, if we need to shift that down a little bit to make it go through the 0.00 and all the other standards kind of follow suit, this sometimes we can get by with. But we should never do really zero shift to these solvents that have very high absorbances. The best scenario is to change the solvent. Don't use that solvent. Or change the method. Don't use that instrument. Use something else. We do not want high signals associated with our blanks, with our solvent systems. If so, then it's probably not a proper solvent to begin with. So the rule of thumb now is to not do these zero shifts. In the software of many of the instruments, you're going to see a zero shift option. And you can check that box in the software system, and it will take this calibration curve and it will shift it down to make it go through the 0.00. So what's the big deal? Right? Why am I going on and on and on about this? Well, let's think about standards for a minute. All right. So let's say that I make a standard and I put in a little bit of my sample and then a whole lot of solvent, right? And this is my standard number 1. Well, then I go and I make my second standard. So I actually put a little bit more solvent in it, or a little bit more standard in it, and then a little bit less solvent. This is my standard number 2. Standard number 3, I put a little bit more standard, and I put less and less solvent in it, right? So what I'm trying to get to is that when you prepare your standards, the volumes of each one of these are changing. Meaning that you're typically putting more and more standard in the volumetric flask, and you're putting less and less solvent in it as you go to dilute it to the line. Well, look at this problem. If I have a solvent, and this solvent is contributing to a signal, when I make my standards, these standards have different amounts of solvent in each and every one of them. I'm not putting the same amount of solvent in each one. They're not consistent. They're not the same across the board. And because of that, that solvent is going to contribute to the signal in different ways. So that's the number one problem with picking a solvent that has a signal associated with it. When it comes to your standards, the standards might line up, but the standards might actually line up in a way that exaggerates the problem. Because you're using less and less and less, or more and more and more of the solvent. It just depends on how you're making the samples. We don't want that to happen. That's going to mess with our calibration curve. It's going to mess with our data. So that's the number one thing of why not to pick solvents from very high signal values. If we do that and it comes out to be a line and we think that everything is okay, or let's say that the line really flattens out a little bit because I'm using more and more solvent or less and less solvent, whatever case that is, this zero shift happens. It's not going to fix that problem. It will force your line to go through the 0.00, but it doesn't fix the problem of the solvents absorbing sample. And it doesn't fix the problem of your standards absorbing differently because you've got different amounts of solvent in them. So never really choose zero shift. Never take the calibration curve and force it down to go through the origin. The rule of thumb now, typically what we would prefer in a lab, is to try to change the solvent. Get rid of the solvent, choose something else that will work, but minimizes the signal from the instrument or the method that you're trying to do. All right? So that's the whole concept of zero shift. It is a term that is used sometimes in a lab, but if someone throws it out, you now know what they mean. You now know what they talk about. For those of you that have worked on our total organic carbon system, this is something that shows up in that software system when you do your calibration curve. It's right there kind of up front and center. It's almost like they want you to choose it. But you will see that if you pay attention to that software the next time that you use that piece of equipment. Our AA also has it embedded into the calibration curve as well. And our HPLCs have it as well. But never check it. Make sure the box is blank every time that you make a calibration standard set and run them. And I think that you'll get some good data because of it. So no to zero shift. Let that be a take-home message. And now you know why.